I was like, oh, whatever.
Yeah, what sucks about the blocking electives, is I think I have an hour from something. I think go right over. So it's in my elective, so I need 13 hours. Which means no matter what I do, I have extra hours. But I plan for that, you could take,
Like unused hours you're talking about?
I'm not sure what it can be, it's unapplied, but it's like an hour and a half.
Oh, dude, I graduated.
150 credit hours, same. But so it, so it just dropped the hour into my electives. So again, I've got, instead of 14 hours in there, I've got 13 hours for like a mod. So you can take lab sciences for 28 hours, and you can take two like math classes, which will get you to 6 and get to like 14, but that's gonna have an extra. That's what I think. Where if I did all, if I skipped lab science and all math electives, then, you know, I'm gonna have 2 extra hours. I'd have to take 5 classes. So over summer, I'm hoping to knock out just 1 block of lab sciences or the first in for you, 2 blocks of lab science.
Yes, who do you have for? Bill?
Yeah, so we can still,
I'm just, sorry, I'm still get that.
he probably has his office hours.
Well, like I said, I want to take it, but part of me wants to take it because it still would boost my GPA.
Yeah.
And part of me doesn't think this. Also, that's my baby.
Yeah, I still haven't even like filled out the FAFSA.
Oh,
But I'll get $1,000 stipend from research grants.
oh, yeah,
So
you're doing,
yeah, it's a number 3.
I'm sorry, what was the game?
So we're looking at 60-degree triangle triples and 120-degree triangle triples. We're trying to find pattern.
I see. I like to hear more.
I think
You guys. Things I wanted to get into study. So now you're well rested.
well rested and well atrophied.
You're ready for the semester. You have no excuse.
Let's just keep our fingers crossed that my car doesn't blow up on me again. And that if it does, the van I borrow won't.
This is the hope. But what is it, Wilson's law or something that says if something's going to go wrong, if something can go wrong, it will go wrong?
That's Murphy's law.
Murphy's law. I guess.
Anything that can go wrong.
Yeah.
I guess she forgot our placards.
Fingers.
Just the keyboard.
Yeah.
She forgot them. Forget them.
There's only 3 students this semester.
Yes.
Big class, big class.
It's much bigger than real analysis.
I don't know, there's at least 3 of us on that, I think. This is me, you.
No, real analysis.
I think that.
It's a 50% increase.
Yeah, I think there's 3 of us at least. I know Brett. Because I know Brett hasn't taken one yet, so he won't be in it, but the black girl, sure. Us. And then I don't know who the other person is.
I think I remember
And of course, as soon as I see Dr. Blake, man, I haven't seen you since last year, man.
Yeah.
You'll,
You think,
big numbers, big numbers.
sleeps like something.
I think maybe after like what we said. But he's also teaching topology or something. Yeah, I'm sure.
How many of you are actuarial science major?
Oh, just me.
Well,
Oh,
that's already 1/3. So,
well.
He's got great expectations for you.
did I email you about the internship? I think I emailed you.
Yes, I think you emailed all math majors about the internship.
Yeah,
I haven't looked at my emails.
let's see. There's an internship.
Like,
There's still time. So I think it's due the 14th. So it's at Unum Insurance if you wanna try. Because it's a internship at the insurance company. If you, I think it would benefit if you are trying to look for
yeah,
it.
I was half debating applying. Even though I'm declared pure math.
I see. Yeah, I think I think it's open to all students, but for actuarial science students, if they really want to work as actuarial,
It was a summer internship. Or how was, I don't remember, was that for this semester or was it for the summer?
let me try to look it up. I received it from other faculty. I felt like it would be benefit our student. So
You gotta apply by June.
Yeah.
it's a scholar program internship.
Oh, you're around.
Yes. It's in
Don't you,
Chattanooga.
don't you have like a, for math major, don't you have a, internship somewheres? I think that's a.
For actuarial science, it does have internship. But we can work around. I think this year there are 2 students, they were graduating, they need the internship credit. So if they can find internship opportunity, it will be good. But if they cannot, I'm probably gonna set up some kind of project to satisfy the requirement.
So for me, could I do this, and count towards that?
Yeah. If
Okay.
you can.
Looks like it's mostly operations, I guess. I just don't.
So it's not geared toward, it's not about actuarial, it could be anything that they want you to do. It's in Chattanooga, so it's not too far. I think it would be a good opportunity if we can. Anyway, it's in your email, so check it out. I think you have to apply on the handshake. It's like that's how you apply. Okay, let's go back to our class. Today's the first day of class, so let's so normally on the first day of class, we'll look at the syllabus. This year we have simple syllabus. So most of us are moving all our syllabus onto this platform. And basically it provides a uniform format for all the syllabus. And for example, you can see the first thing will be instructor information, the title of the class, email, name, phone number. And then the course information, this class is the second class in the probably statistical sequence. We're gonna learn chapter 5 through 9 of the textbook. And we're gonna talk about, this is the second part, so we focus more heavily on statistics. But chapter 5 are mostly probably, and the rest of the chapter focus statistics. And we're gonna talk about hypothesis testing, likelihood ratio, non-parametric test, normal distribution. They're a little bit short. Don't know if we are gonna do multivariable normal distribution. That was a textbook. It's the same textbook. If you have the day one ready thing under course resource or day one ready, inside day one ready, you can find the textbook. It's not even. It's weird. Yeah, I'll contact them about the day one thing.
Discount price.
Okay, so the main content of on the syllabus are, let me turn this on. So the catalog information about, that's about the textbook. You see that on the left column shows all the items, which allows you to go there very quickly. The core impact. This is not a core impact class. That's statement. Then there's grading. We have 3. All right. Oh, that's what I did. I think it started 2 years ago. I changed the class arrangement. I removed some of the major tests and use the weekly quizzes instead. If we have 2 days in a week, we'll have a quiz on that Wednesday. If we like next week, we have the MLK holiday. We only have a Wednesday, so we don't have a quiz. This week, this is the first week. We don't have a lot of new content. Like today is the first day, so we won't be able to have a quiz this Wednesday. So maybe for the week after next week, we'll have a quiz that Wednesday. So pretty much we're gonna have a quiz whenever we have 2 days of class in that week. And so we're gonna have multiple quizzes throughout the whole semester. And I do this because quiz don't take up the whole class session. If we have a test, this whole class session is a test. If we have 4 tests, they're gonna take up 4 days. And then we also have to spend 1 day preparing for the test. So I feel like that's really too time consuming. It takes up too much time. We won't be able to finish the content. So we're gonna have really short quizzes every week. The quiz questions are from the homework question. So you guys will work on whatever section we're gonna work on. There will be homework from the book. And that question will be possible question on the quiz. And I normally have 1 or 2 questions for that quiz. So then the quiz will be really short. That will give us more time for the content. So that was fine. So we're gonna have weekly quizzes, a midterm, a final exam, and then homework from the book, and then class participation also 5% grading. So that's really how the classes will be assessed. Any question? Okay, so we don't have to worry about quizzes for the first 2 weeks, and then starting the 3rd week, we'll start having quiz every week. And it was about the grading and the learning objective, or what exactly we're learning. I really like how it's being phrased, focused on a lot of them are chapter 5. Join a marginal probability and mass function or probability density function. These are from chapter 4 or 5 of the book. Find the means, variance, and correlation coefficients. That's chapter 4 or 5. The Chebyshev equality was 5.8, so that's chapter 5. Hypothesis testing is chapter 8. So we do hypothesis tests, Wilcoxon test and hypothesis testing. They're both chapter 9 of the book. Of likelihood ratio test is also chapter 8. So focus on the earlier section more than the later section. Any question? Chapter 8 and 9 are on hypothesis testing. Chapter 6 and 7 are the estimation confidence. And then simple that to 10 inferences. So hypothesis testing confidence. So either both inferential statistic method, that's true statistics that we had before, explore relation between two variables. This is ranging a couple chapter to explain relation between two variables. If we try to study relation between two variables, it depends on what kind of variable. If it's two quantitative variable, we have to do the scatter plot. We have to do linear regression. If it's two qualitative variable, we have to do chi-square tests. If it's one quality and one quantitative variable, and we might have to do a ANOVA test. So it's depending on what kind of variable. That will dictate how we study the relation. The last one is use appropriate technology to generate data, and that's simulation, or analyze data. That's the statistical procedure. So in this class, because I don't want people have to pay for the software, we're using R. Did you guys try R last semester? No? Okay, so I guess we will have to learn from the beginning on how to use the software to do statistical work. Okay, so that's the learning objective. And let's move on to attendance policy. I certainly hope that we will be able to attend class regularly. But other than that, you can also attend online. I've been providing ways to do that since in my other classes too. If you've had my other classes, like today we have the January 12th MS 4702 class meeting. That's the link you can click on to open up, and this leads you to the Microsoft Teams app. I already have the app open, just this, so that. So you have to log in and open the Teams app, and then log in and open the Georgia view, and then this link will actually work there also. Okay, so this is how you can attend classes virtually. So I hope by providing a way to attend virtually and in person, we can have we'll be more likely to follow along and attend class without missing too many classes. Any questions? Right, the class content, whatever we're covering that day, whatever PowerPoint I was using, I put it in the same place. So it's easy to find out what happened each day. Any question? Inside content, you can say week 1, week 2, week 3, week 4. So the weekly schedule is already listed in content on Georgia View. And then below there were the rest of the stuff that I guess they were small. They belong to the same place. I have a folder. Plus, to learn the R, I provided a couple of coding, R coding. Any question? So that's the attendance policy. Late work, if you miss a test, we have 3 tests in this class. So if you make up exam, we do it at the testing center upstairs. Well, this is already upstairs at the second floor of this building. It's testing center at 201. That's the location, and that's also the method for any possible main test. Right, and then AI. I can't not see where 100% prohibiting AI. But since we're using R, we're already allowing students to use computer, right? If you were doing heavy calculation, you will be using R for the for computation already. So on test days, you are allowed to bring your own computer. This classroom does not have a computer. I guess you have to bring your own computer for calculation, or I think that's the only way we can use R. Right? I guess let me try to explain a little what's R. R is a statistical software that's very similar to many commercial software such as SES, SPSS. So, but it's a command line, so you have to write your like line by line command. So it's not the same as Excel. Excel is another way of entering data and doing statistical work. So we're still using it, but it will be easier to have data because Excel is so organized everything in terms of column and row. So we do utilize Excel as a way to format data, way to record data and formatting the data. And that's the software. If you want to install the R on your own personal computer, you will download the R. When you try to download, it's a couple of websites, a couple of locations. The easiest thing to do is search multiple locations. Here you can get this website. You can download the Windows version of it. Normally, I would recommend you install a base version of it. And then go from there. Or if you don't feel like putting something that has a big size software on your own device, you can also do this run R online. So you run R command without installing anything. Try to get rid of the example code. So installing it on your device made it convenient because it opened the whole package. And once you have it run, it would. I want to show you how it looks like. But this is having the language in a single window. For example, we can enter a data set x equal C as in chain 1, 2, 6, 9, 8. Okay, so that's the data set. You want to find the average. You go mean x. So we'll calculate the average of these numbers. Okay, 5.2. So if added all together, the total average will be 5.2. Another simple language will be the summation. So X is now your data set. So summation will be, click on run, it's 26. So obviously if you divide it by 1, 2, 3, you divide it by 5, give you the average. So 5.2. So because the average of these 5 numbers is added all together divided by 5, same, right? There's other calculation. You can find the variance of the data set. VAR is the variance. Variability is being measured by variance 12.7. We're gonna do a lot of things with this. I find it very convenient to calculate something. So every single number added square added together, summation of x squared should be a larger number since the square is large. So 186, quick calculation. Okay, so this is without installing anything. Now, if we install, I have it already downloaded. So if we install the R, this is how it looks like. I don't know if it's finished installing. Okay, let's see if it's installed on this computer. because at my office computer, I have to have permission to install. This computer, I think you can install. Customize. We don't want to customize. Just want to show how it looks like when you install the R code on your computer. Do you have any question?
So is the base package going to cover all of our needs, or are there? extra
Whenever
packages?
you have other package, you can always install it after. So you
Yeah.
can look up the package, install whatever you need. Instead of installing a lot of things that you may or may not need, it's easier to just get the base and
Yeah.
add as you go.
All right.
So this is finished installing. Once we finish installing, it shows up here as, you see the R, the big R there, that's the software. But when you open it, some people find it difficult to apply. You see, it's just that they give you a command line, but prefer having something called a source code or new script to open a script. So what is a command line? Command line like this, which is when you do this is all command line. But if you do it software on the command line window, it's called a console. Our console, I guess I can do the same thing. Copy it over here. So if we do a calculation like this, you have to push enter. It shows you 5.2, so it's quicker than the online version, right? It's a little quicker. But the problem is that if you finish that line, it goes up, and we no longer have, so we no longer have it, and then you have to write a command again. So that's why we might want to have a script. It's also somewhere. There's multiple things in here, so they don't panel. They go like they're like all over the place. So what is script? As an editor means that you can edit a bunch of them and do it one by one. So we can have all these in the same place. In the script, this is called a script, and then all these, you can do it one by one, which is, I think it's control enter, control space. Control R. Okay, you can also run line by line. So whatever, this allows you to save it. The problem with the console is once you finish running that sentence or that command, it's no longer there. The next time you want to do this, you have to copy it. So you can't now go back, right? The cursor move on to the next opening, you can't go back there, do it again. But the script allows you to save this, go up there and save the scripts. So once you save it, save it in download. Right. I'll just call that example. Right. So it's called the ex.r, which is a script, and you can let it run line or selection. So I will select and run the selection. You can go back here in the console. It shows that command is being executed or run. You're gonna say whatever you're running, it will show. It won't change the script at all. Script will be a static. I don't know if this is a little too much on the first day of the class, but with it. See, so the window kind of cover each other, which causes a little bit hard to find them. So there's this thing called the R Studio. R Studio. So another software which provide a front that has all the stuff organized a little bit better. So want to download it. Where was it? It was a lot easier to download before. They changed it, called Post-it, but it was really RStudio.com a while ago. I think it started going. Download RStudio. We want to start with something that we work on our. The install R we already did, and then install the RStudio. Let's download it first. So this is what I would use on top of R if you want to use it on your computer. There's other ways to do this, but this is the easiest way because it looks better. It's still downloading. Anyway, and you can see if we only have the R, it ends up being difficult to use. You can rearrange them to pair them together. Okay, and then you can choose edit and run all of them. Okay, if you run all 5 language and 5 sentences, in the console, it shows you the result after. But then you see the separate window, and then you have to have these 2 arranged. But in R, let's see. Let's install the RStudio. I'll show you how it looks like once the RStudio is being applied. So there are a couple of other things that's also in R, but it doesn't show you. You have to dig into the system to find them, like where was the memory, how many variables have we defined and saved. So if we find them in the view, you have to find them out, dig them into the system, and listing the object that we did. They won't list them. All right, so I find it a little bit awkward to use by R by itself. So I mean, someone recommended it to me, so we would put R installed. R is the calculation base. RStudio is like putting utility on top of the R. R is the calculation machine, but RStudio is the one that rearranging everything to a lot more easier way. So let me see. I think I finished installing RStudio, but I can't find it. RStudio like this. Okay, so this is the new version of RStudio. So this is the RStudio looks like. Over here on the panel, everything. This is the console. This is an environment, and over here is everything related to whatever you're doing. So, for example, over here, we will go file, and I'm gonna new file, new R script. And earlier I had those calculation I have over here. I'm gonna use that in the file. So that's your script. And below here is the environment, and you can run them one by one. I think it's this. You see it's being executed. This is the console. The first sentence or the first command is putting all 5 number into that data set. This is a pure input language. There's no outputs, right? The second sentence is calculating the mean. That if you put your cursor there and do Control Enter, it will run that language, and immediately down there you see 5.2. Are we okay? I don't know if that's too small. So you can run it one by one and Control Enter, Control Enter, Control Enter. So whichever one you want to apply, you want to do it again. So we go back here, and then I want to calculate the mean again. So you go mean and Control Enter, it will execute that language repeatedly. So this means that the same thing you can run as many times as you want to without having to enter that command. You got to say, so you can do the same thing without having to copy and paste. Another thing is it shows you how many things that's already being defined. We call this is our X data. It's over here. X. It says numerical. We got X is really being entered as a vector. So it's a 5-element vector. Those are the elements. And you can do other things. For example, let's say y equal to, you can use words like the red, and then the red is a special letter. And if I put a letter there, weird. I wonder if I do. Okay, this is not there when the last time I was using RStudio. I've been using the online R for a long time. And then maybe yellow. Okay, that's interesting. Red, blue, green. What if I put white? Okay, there's nothing. So we can run this. Control Enter. So it's say Y is a character, right? It's a vector of character with 5 characters. So over here in the environment, it has anything that you put into the memory you define. So these 4 panel shows what's all that's connected to the script. And I guess we can have a pie chart of the X. Wonder if this works. It's okay. So basically, use the X data as the size of the pie, and use the Y, it's all those words, as name of the pie. And I guess the color didn't. It was weird.
That's yellow, red, red, yellow.
Okay. So it didn't follow the words. So even you made the color that way, when you try to do the pie chart, it didn't follow whatever the labels. Alright, so anyway, so this is what R is capable of. But you don't have to install if you don't want to have that memory burden on your device, because it's a big software. It will take some space on your computer if you install it. But I would say it's kind of convenient, and there's a lot R can do. The online version won't be able to handle some of the, like, if you have a file, R can read the data in your file. Maybe you have all your data in Excel. R can pull the data from the Excel file. And that is something that online R cannot do. Online R, you have to input your own data and do your own calculation. If we have a short code, then the online R will be fine. But if you have a heavy, a large data set, then you may have to install the software on your computer. But it's a really cool way to do statistics. It does much, much more than what Excel can do. Any question? You can still use Excel as a way to save your file, but the calculation R does a lot better than Excel. Anyway, so we are going to try to use R. I won't be able to install these every single time, because this computer, once the computer once I log out, once the computer is closed, any software I install is not there. So next time we're using R, I have to install it again, which is why I decided not to install them. In class, when I do the calculation with R, I will be using the online R, online version of R. Just look like this. How does it run any R code you like? So, this is an online software that we can do some calculation. Question. So we are using a little bit of software. Other than that, we do most of our own work. I don't think AI can answer all questions. I will try not to use AI in this class. emergency instructional plan. The class schedule is posted under content. So what we try to cover every week is there. So we plan on trying to follow that schedule. If there's any changes, we'll try to announce in class and I'll send out announcement after. Any question? The rest of them are common policy, course policy and procedures. Something that we all have about the care team, about the Title IX, about weapons on campus, student activity. Here that says you can borrow a laptop from the library. You can also visit the virtual reality. Any question? Okay. Right. So that's the syllabus. You know where to find it. So a simple syllabus on Churchville. Let's look at what we're gonna do today. So we're gonna continue where we left, and you guys were in the 4701 last fall, but
I like this class so much, I took it, taking it again.
okay. So I was thinking, where do we pick up? Because we had this together, but then this is reviewing again. Right, I guess we can start from the beginning. Okay. So the class we'll try to cover chapter 5, 6, 7, 8, and 9. But chapter 5 is a bridging chapter. We had chapter 5 in 4701, and now we are in 4702. So we're gonna review some of the stuff in chapter 5. The title of chapter 5 is distributional functions of random variable. So basically, random variable itself is the random variable produce random data, and function of random variable is also random variable. So we're trying to find out the distribution of whatever the random variable resulted by the function of random variable. If you look at the content of the chapter, 5.1 focuses on function of one random variable. 5.2 focuses on function of two random variables. 5.3 focuses on random variable, function of several random variables. But we do add this added thing that saying those variables are independent from each other. If they're not independent, it will be super difficult to talk about several variables together. 5.4, we look at a different method to determine the distribution. The method called moment generating function technique. 5.5 is a focus on normal distribution. A lot of time, the functions that we mentioned in the previous section, they end up having something that has a normal distribution. So you want to look at those situations where normal distribution will be applicable. And 5.6 is one of the major results in statistics. It's called the central limit theorem. 5.7. That's again emphasis on normal distributions application. Central limit theorem is one single theorem that made normal distribution very, very important. Right, 5.7 is the approximation for discrete distribution. We can use normal distribution to approximate a couple of discrete distribution, namely the binomial distribution and Poisson distribution. 5.8 is the traction ability that we mentioned in the linear outcome. So that's the section in chapter 5. So let's start with 5.1. I guess this is pretty much reviewing. So we probably won't be very slow on the process. So 5.1 is talk about function of one random variable. For example, you have one variable that's called x. Assuming we know everything about this variable, we have its probability mass function. Assuming it's discrete for now. then a y, which is a function of x. So y equal to ux, meaning that we got a formula calculated using x that causes, that's how y is being defined. So now we want to find out what is the distribution function for y. So we know the distribution function for x. Let's find the distribution function for y. So how do we do it exactly? So the main idea is you want to find the connection between how x behavior to how y would behave. And that is, maybe it will be beneficial if we can find the inverse function of the y. If y equal to ux, and we can solve the x from that formula, so assuming the inverse of this function is v, I don't have it over here, assuming that x equal to v of y. So x had that density function. So then this x, it is a variable, so you can do a substitution, x equal to vy. Since x equal to vy, then vy can be plugged into the fx to replace the x, right? So that will make it possible for us creating a distribution function using the fx. All right, so that's kind of some of the ideas. Now here is the example that we had in this section. Starting out with a discrete example. And this is saying that x is uniformly distributed among all 8 numbers. So they're equally likely, -1, -1, 0, and then 1, 2, 3, 4, 5. All 8 numbers are equally likely. So the probability is 1/8. And now we have this new variable. New variable is y equal to x squared. We want to know what is the probability for y. Probability for x is 1/8 for every x value. So what is the probability of y? What is probability y equal to 1? What is probability y equal to 2? And so on. So in order to have that, we need to find a match. And here we are. Okay. So in order to find the relation, since the probability for all 8 numbers are equally likely, so it's 1/8 for all of them. And then, and you want to find, this is discrete, so it's easy to set up a table. For x, you can calculate y. Y equal to x squared, so -2 squared, 1 squared, 0 squared. So each one has a square. Now, each one also have its own probability. So this 1/8, 1/8, 1/8. However, there's 2, 4. So that raises the probability for 4. Probability for y equal to 4 would be 1/8 plus 1/8, which gives us 2/8 for y equal to 4. And there's also y equal to 1. There's 2/1. So 2/8 instead of 1/8. That's the only 2 scenarios y would have a higher probability. The rest of them will still have 1/8 for their probability. So y equal to 0, 9, 16, 25, the probability is 1/8. So having that table really clearly made us to identify those probability very quickly. Are you okay? So I would really recommend having a table for any discrete scenario. And then there is also the one that is impossible to have a table for. So this is an example for Poisson distribution. What is Poisson distribution? Poisson distribution is the number of occurrences that follow the probability, Poisson probability. For example, if something have an average occurrence of 4, then the probability for x occur 0, 1, 2, 3, 4. So 0 start from 0 and then goes on to infinity. The probability for that x value is, this is discrete because there's no 1.5, there's no 2.2. All right, so the probability 4 to the power x e to the -4 and then x factorial. This is a Poisson probability formula that we studied in chapter 2. But then the question is, if we already have a probability for x, can we find a probability for y if the y equal to root of x? Now, x is an integer. X is number of occurrence, which is 0, 1, 2. Occur 0 times, occur 1 time, occur 2 times, 3 times. X is the number of occurrence, which made it has to be an integer. but y equal to root of x, which means y could be a irrational number since it's a root number. It's a root of an integer. So we want to know what is a probability for y. What is probability that y equal to root of 2? What is the probability y equal to root of 5? And so on. And the answer is they're 1 to 1, right? They're supposed to be. So from this probability to this probability, all you have to do is to find the inverse. If y equal to root of x, then x equal to y squared. So then this probability can be directly converted to the probability about y. What we did is do substitution. So x equal to y squared, so that's y squared. 4 to the power x become 4 to the y squared. And e to the negative 4 to e to the negative 4. They're just number. X factorial become y squared factorial. And that's the probability for it. But the only problem is that the y, g of y, what is that equal to y? Y equal to root of x, so it has to be a 1-to-1 partial. Root of 0, root of 1, 2, root 3, and so on. So that is the exact match between the two. That's the discrete case. Any question? Notice that finding the inverse and directly substitute the inverse, that's all we have to do. There's no differentiation. We do the differentiation only for the density function because density function are not probability. Density function is a derivative of probability, right? Right? That's why we have to do differentiation. This one, there's no differentiation because these are probability. That's a probability for x equal to a number. This is a probability for y equal to a number. If this probability, if you equal to this probability, if you don't think about the x and y differences, they're identical. Any question? Okay. So that's discrete case. All right. Continuous case is more complex because for continuous case, we don't describe the probability because it's going to be all over the place because it's a continuous. So for describing continuous distribution, we would this is all drained up. We would find out the edge of the probability or the density function. I guess I'm going to have this. I hope I carry them. Otherwise, I won't mark actually use. I really didn't carry any marker with me. You do? Thank you.
They should be good.
Yeah.
That's all it's doing.
All right. So basically the discrete case is this. Here you are 1, 2, 3. For discrete case, you're going to find the probability for 1, probability for 2, probability for 3. So you're going to find the probability 1 by 1. Probability is basically this, and the weight of it is really just 1. But for continuous, the probability are not going to be isolated by itself. That's why it's called continuous instead of discrete. It's like this. Okay, so the probability is really the area on the curve. That's probability. That's probability. So if you want to describe the behavior of continuous distribution, you're going to find out the function, like a function like this, and call it f of x. This function, we give a name, we call it density. It's the edge of the probability calculation. You want to calculate the probability to find this edge and this edge. So probability for the variable between b and a would equal to integration from a and b of the density function. Because f of x only describes the edge of the probability, not the actual probability. So if you want to find the probability, you have to integrate the density. So that that density function is a derivative. We call this f of x. Probability is f of x. Then this is actually the derivative of the probability distribution. So anyway, so because of that differentiation process, we will have to differentiate whenever we need to identify new density. Okay, so the idea is you start with a known distribution. This is called X. It is a variable that we know. We also know the density function. Now we have y equal to ux. So y equal to a function of x. The u of x can be a lot of different, a variety of ways to define. And y is being defined as a function of x. And then now we want to know the behavior or distribution of y. And you have to answer the question, if x is continuous, how is y? Is y discrete or is y continuous? The answer is they could be either way. So for example, y equal to 1 if x is positive, y equal to 0 if x is negative. And that means y equal to 1 or 0. That means y is discrete. If that's the case, then you're going to calculate the probability one by one. Probability y equal to 0 would equal to the integration of the density function, whatever is equal to 0, and probably y equal to 1. So you have to calculate it one by one. All right, so that's one scenario, which should be a little simpler than do all that. Second situation is x is continuous, y is also continuous. For example, y equal to x squared. X is continuous, y equal to x squared would also be, I mean, the composition function of a continuous function would also be a continuous function. So that's another situation. So if y is continuous, then a continuous function of a differentiable continuous function will have a derivative. So what happened is that if y is continuous, you would utilize the original density function of x to construct the density function of y. Because the close relation between x and y, then the formatting of the density function for y will have a lot of similarity to this. So what we're going to do, we will look for the inverse. I mean, this is the CDF approach, but that's trying to explain the logic behind it. Suppose the probability for y is f of y is probably y less than y. Again, fy is a distribution function. Distribution function is a integration of the density function. So if we find the distribution function, derivative distribution function will be the density. So by definition, fy equal to probably y less than y, and the y equal to u of x. So u of x less than y. If we can find the inverse, then u of x is less than y. If the inverse is vy, so we find the inverse of both sides of the function, that x is less than vy. This is assuming the inverse function is increasing. So this is the probability. Now this probability is the integration of the density function. So probability of x less than any number is the integration of the density function. So then we will have this function would be the integration of this from -infinity to vy. So this function can be differentiated. So we find the derivative of this function, which is equal to, so the density function for the y equal to the derivative of this function and equal to the derivative of this function. When you're differentiating is derivative of this function would be the density function, right? The distribution function for x equal to this. And then the inside function vy, you have to multiply the derivative inside function. So essentially what you have to do is to find the inverse, such as y equal to u of x equal to v of y, x equal to v of y. So x replace the x, f of v of y times the derivative of v of y. The reason that we multiply the derivative is because of chain rule, right? In calculus, if you plug in something into the inside and you have to multiply the derivative of the inside function, that's chain rule. Because this is really a differentiation process, finding derivative of the composition function. Any question? So that become the method. This is using the CDF functions, cumulative distribution function, CDF, using the CDF approach to prove that putting the inverse function in the original density and multiply the derivative of the inverse, right, derivative of the inverse function, that will be a good method in order to determine the density of the new function. Anyway, this is the example in the continuous case. We started with the gamma distribution, which the formula is what we did, what we learned in section 3.2. And then we have this new variable y equal to e to the power y. And then what will be the density function for y? So density function for x equal to, I guess we could write on top of it. I realize that it's okay, so we start with a given distribution. So we have a variable that was given, and then this variable has its own density function. Now we have this new variable. The new variable is y equal to e to the x. So we need to find out a distribution for the y. We need to find out what exactly is the y. Instead of fy, let's not use f. We use g of y. So we're hoping to find exactly what's the behavior y. So based on what we already have talked about, because this relation between x and y, you can quickly find the inverse of y equal to e to the x. So the inverse of the exponential function is natural log. So natural log of y equal to x. That's the inverse. So we would take the original density function and plug in that into the density function there. I'm trying to get rid of it. So what happened is if you put in the x equal to natural log of y in whenever the x is this x and that x, you'll be creating a function like this, f of y, g of y. G of y is equal to 1 over gamma alpha. I'm copying theta to the alpha power. And then x, we're not writing x anymore. We write natural log of y, right? And then to the power alpha minus 1. And then e to the negative x over theta. Instead of x, we write natural log of y over theta. Right? Everything is copied over from, did I move something? So that one, all the x's are replaced by ln of y. Now we have this. Okay. And then there's one more thing. We have to multiply the derivative. You're gonna look at this inverse. The derivative of this is 1 over y. So we multiply 1 over y. And then we're all set. So that's how you determine the density of the y variable. All you have to do is find the inverse, plug in the original density, and then multiply the derivative inverse. And that'll be what we have in the answer. Any question? Okay, so that was a method. Find the inverse, plug in, do a substitution, and multiply the derivative of the inverse. Over here, explain the reason for that. So the cumulative distribution for y is g of y, capital G, which equal to probability y less than y, the y equal to e to the x. So x is less than natural log of y. And then therefore we have that probability should be calculated by integration of its density. Now putting to calculus, the derivative of this function will be putting the upper limit function into the variable part. And then multiply the derivative of that inside function. So the reason for this is the fundamental theorem calculus. So that's what happened. Any question? So I'm pretty much using this time to repeat things that we were talking about it before. Hopefully it will help out to refresh memory. All right, this is another example called log gamma distribution. is when the logarithm of the variable is a gamma distribution. That's why we call it log distribution. And here, the log distribution is exactly what we mentioned in this example. It's the y function. So y equal to e to the x. The x equal to natural log of y, and then x itself is the x is a gamma distribution, but the y has a distribution. And we can also find the mean of this function and the variance of this function. This is a special distribution. Any question? Logarithm of y function as a gamma distribution. And this is a fifth example, which is we start with a uniform distribution. X is a uniform distribution, and y equal to tangent of x. So this example is showing that suppose x is a uniform distribution, then the tangent of x has something called it's called a Cauchy distribution. Cauchy probability density function. So and what we have here is very similar. Do you have any question? So we did very similar things like before. Here we have a uniform distribution, right? So what is a density function? This is A, this is B. B minus A. I guess we can review the uniform distribution and then start from there. We pretty much repeat everything that we were talking about with a special distribution. All right, so in this example, we have a variable that has a uniform distribution. So for this, we have a given density function. That's the CDF. CDF is a little longer, but the density function would be slightly shorter. Density is f of x equal to 1 over, I don't know, for uniform distribution on A to B. The density function would equal to 1 over B minus A, right? I wonder if you remember, because a uniform distribution means that from A to B is uniformly distributed. So it would be the same likelihood, right, from A to B. Now, the total area under the density function supposed to equal to 1. In order to equal to 1, this side is A to B. So this side has a distance of B minus A. So this height have to have a height of 1 over B minus A. That way, 1 over B minus A, which is a height, multiply B minus A, the total area equal to 1. I mean, probably equal to 1, right? Under this curve, it has to equal to 1. So now, because the height equal to B minus A, so the density function has to have this height has to have 1 over B minus A. So the density function here is 1 over, that was A, that was B. So pi over 2 minus negative pi over 2 is pi. Right? X is, whenever X is between the pi over 2 and negative pi over 2, then the density function equal to this. Of course, it also has to equal to 0 anywhere else. Otherwise, it's 0. Only when it's between these two that we have this. Are we okay? All right, so now let's talk about this new variable. New variable says y equal to tangent of x. So if we want to find out the density function for y, it will equal to, now we have to find the inverse. The inverse for this will be x equal to arctan of y, or tangent inverse of y. That's the inverse, right? I'm gonna put the inverse, and I have to, I think whenever I move around, somewhere in there is not connecting well. X equal to arctangent of y, so I have to put this into the inverse function, put it into the density. but there's nothing in the density, right? The density function is constant. So the density function will be 1/pi with nothing to enter. But we do have to multiply the derivative of the inverse, right? What's the derivative of R10? Derivative of R10 is 1/1 plus variable squared. That's why we have to multiply by 1/1 plus y squared. Right? That will be the density function for the y. Yes. So 1/pi will be part of the factor, but then you multiply the derivative of the tangent function. And that's why we have this answer. So it's 1/pi times 1 plus y squared. And this is a function that defined from -infinity to +infinity because y equal to tangent of x. So the definition for x is limited between -π/2 and +π/2. That's the x. X is between -π/2 and +. It's an angle. However, y equal to tangent of x. So tangent goes -infinity to +infinity. So y actually being defined from -infinity to +infinity. Right? The original density function is finite, have a finite domain, but the function of the variable y equal to tangent x actually have a domain that's -infinity to infinity. Basically, this projection y equal to tangent x project from a interval between -π/2 to +π/2 onto the whole number line. So that of having a finite number line, interval, finite interval, we have infinite. So the domain is now 0 to infinity, and then this is our Cauchy distribution density. Any question? And that is one that we keep mentioning it because it's a special case. This density function, when you integrate 0 to -infinity to +infinity of 1/1 plus y squared, the whole integration, I think it equal 1. That's the definition. That's the requirement for any density function. Any density function, if you integrate it on its own domain, the whole area below the curve should be equal to 1. But if you want to find the expectation of this, it doesn't have expectation. Its expectation is an improper integral. It doesn't have a finite value. That's what's kind of interesting to say. Sometimes the integration, the mean of the random variable are not guaranteed to exist. And that's a special case. Try to make this. That's why people keep mentioning it, because this is one of the scenarios where the mean of the y value, because the mean of the variable is e, right? E of x or e of any variable should be the integration of this variable on its domain. We're going to do -infinity to +infinity. Now e of y is y multiplied by the density function of y and dy. So this is how you find expectation, right? Expectation of the variable is whatever variable you have multiplied by the density, g of y. Are we okay? I guess whenever I was sitting down, you can't really see it. But then you can see what happened. The g of y is 1/pi times 1/1 plus y squared. So now we have y times 1/y squared integrated from -infinity to +infinity. The integration is infinity. It doesn't have a finite answer. So this e of y, it does not exist. That's why people keep mentioning it. It does not exist. Most of the random variable, they do have a expectation mean value. So does it mean it has no center? It does have a center. The center of distribution is at 0 because the density function is symmetrical about 0. It's an even function. Density function is an even function. So that number in the middle of the 0 is not going to be its expectation, but it's the median of the distribution. So this y variable, y equal to tangent of x, where x is a distribution, the y variable has a median. it does not have a mean. The special situation, right? If this example. All right, let's move on from that example. And then a couple of other topic in this section is, right, what if U is decreasing? If U is decreasing, then the derivative of U will be negative, and therefore the inverse function will also be decreasing, and derivative of that function will also be negative. So what will happen is whenever you want to try to find the inverse of it, you plug in the inverse functions and then multiply by the derivative of the inverse. Now derivative of the inverse, this is decreasing, the derivative will be negative. We don't have negative, we don't want to have negative number in the density. So because negative A prime is negative, so we put a negative number there. Or another way to say this is that we put an X value on the derivative of the inverse. So that this is saying that the U function, y equal to U of X, U function, if it's increasing, we can do it. If it's decreasing, we can also find its density. All we have to do is make sure to have the absolute value. But if it's sometimes increasing, sometimes decreasing, then that will be a problem. So if the y equal to U of X, if that U, if it's not monotone, then we have to do it case by case. So, all right, 5.1-1 talk about how to use the inverse of the cumulative distribution as a way to do transportation. The first results, there's the 5.1-1, there's 5.1-2. Two of them, they actually achieve different things. The first part is, suppose you have a uniform distribution, and what we can do is we can use the inverse of this distribution function, f inverse of y. That will allow us to create a random variable x. X equal to f inverse y. X has a distribution function that was f of x. So basically this result saying you can simulate the variable. You can create any random variable or simulate a random variable that has your targeted distribution function. So f is the increasing function from 0 to 1. If you identify it as the inverse, then x equal to f inverse of y, which will be a random variable if the y itself is a uniform random variable, then it will have exactly the behavior. The distribution of the x will be f of x. So this is like whenever distribution you want to simulate, you can use this as a simulation method. For example, so here that was a proof of this theorem. So one of the things we can do is to simulate the Cauchy distribution. Okay, so what you can do is you begin by having a uniform distribution variable from 0 to 1. So from 0 to 1, anywhere, any number between 0 to 1 is your option for the y variable. And then what you're going to do is you would find a Cauchy distribution. If you want to create a Cauchy distribution, then it would be tangent. It's tangent of y. But instead of tangent of y, we did x equal to tangent pi y minus pi over 2. That's the method for creating the x value. And then when you do that, x will have a Cauchy distribution. So this is it's easy to simulate uniform distribution. R can do it, but it's not so easy to simulate the Cauchy distribution. So then, example. So here we have, we can use the appendix in the book to simulate any random variable between 0 and 1. Those are the table values in the book. And I'm going to do 0.8675, 0.779. 0.7408. Those are all number, and These are from the table, but you can use this as a number that simulated random variable from 0 to 1. And then what we're gonna do is we take those number and put it into this formula. Tangent pi times 1 minus pi over 2, and creating this variable. The Cauchy observation simulated using all those numbers. One-to-one correspondence. That was example on how do we simulate targeted distribution function. This is a method to creating a Cauchy. Any question? Okay, we can also do it with our computer if you want to. Creating random variable always being a topic in computer science. Let's see. Right, I guess this is a try to creating a random variable from. Okay, I think I remember the number. It's wrong. Are we out of time?
Yeah.
Okay. Well, look.
Go ahead, I'll let you, for example, 1 and 2.
Okay. Let me go back to it there. R has own a random number generator. It's called R norm to identify distribution. Uniform distribution should be R unit 1. Yes, I remember the function name. Now it's a random number generator. We'll do it later. We'll come back for how do we do a simulation with R. And that's it for today. I hope it was okay for our first day. I'll see you Wednesday. Thank you.
Like that R studio would have really helped us in this.
So people with the R studio. Covers.
I'm just gonna see if the laptop takes it. What's your name? Greg.
Oh, Greg.
I don't know. Good. I'm feeling that I'm gonna get to know both y'all pretty well. Well, already pretty.
Good to see you, sir. Glad you made it through last night.
Thanks, Alex.
Very.
Okay, I'll see you all later. Okay, more classes today?
No, I gotta figure out the next 5 hours. Okay, I'll go home and do some.
I'll just pull ups for the next 5 hours.
That's a good idea. Why did I, see, this is why you're my friend. You got me think out my life choices.
Maybe some dips thrown in every once in a while.
I gotta match the amount of dips to pull-ups.